Now that you got a good sense of what we mean by radiative forcing or forcing, let's put it together in terms of natural forcings that I already mentioned, like volcanoes, and anthropogenic or man-made forcings like greenhouse gases, aerosols, and so on. So this is an image, a figure showing excuse me, effects of volcanic eruptions. So total measurements of solar radiation transmitted at Hawaii's Mauna Loa Observatory. It's showing solar radiation transmitted in terms of percentages, so how much blocking is created. So you can see that there are few volcanic eruptions in this record from way back in the 1950s. The Ogung, which created a little perturbation. After the eruption, you expect a lot of aerosols blocking sunlight, creating solar dimming. The big one occurred in El Chichon in 1982, which also happened to be a big El Nino. Pinatubo was 1991, and there was an El Nino at that time as well. So you can see that solar dimming happens and then the system slowly recovers. And this can also be seen here as Pinatubo's ash plume, which was one of the bigger ones in recent times. And depending on where the volcano is and how powerful it is and how much of the ash and chemicals it's throwing up, a lot of it can get into the stratosphere, which we haven't defined yet. It's the part of the atmosphere above the so-called troposphere. We will see it is called stratosphere because it is stratified, and it is stratified because it's not mixed. There is not much weather, so things that get into stratosphere stay there for a long time, and they get distributed, and they can create reductions in energy, sun's energy coming into the lower atmosphere. And of course you can also see the impact of the aerosols on sunrise, sunset, and generally the skyline. So this is a photograph from Space Shuttle over South America taken on August 8, 1991, showing the dispersion of the aerosols from the Pinatubo eruption in two layers in the stratosphere above the top of cumulonimbus clouds. So you have the cumulonimbus clouds here, which are all in the troposphere, which in the tropics is about 12 kilometers high, and it's very hard to inject things directly into the stratosphere across the troposphere stratosphere boundary, which is called tropopause. We will see that later on. But tall hurricane clouds and storms can puncture through, but here Pinatubo put a lot of ash and aerosols into the stratosphere, and you can clearly see two layers created by these emissions from the volcano. What do volcanoes actually do? It turns out that they can change the energy balance quite a bit. Global surface temperature change here near the time of 5 volcanoes producing the greatest optical depths since 1880. Optical depth is a measure of the aerosol's impact on transmission of radiation. So this is showing Krakatau, Santa Maria, Ogung, El Chichon, and Pinatubo. What is done here is that individual volcanic eruption causes global perturbations, but to separate its impact from everything else that is going on, like an El Nino that I mentioned, or monsoons, other things going on, it is better to take the composites over several El Ninos, start a few years before an El Nino happens, and you can see the natural variability of the temperature around some baseline that we always tend to use to look for anomalies, because impact of something is best measured as anomalies, right? So impact of volcanoes. So there is no volcano, so some natural variability is going on in all these years that are put together. Composited means all those years are taken together. So each volcanic eruption year is considered 0. You go 3 years before and 6-7 years after. So you can see that when the volcanic eruption happens, there is a cooling the temperature at the surface cools by measurable amount. This is global mean, so I have to be careful. It's a substantial change, even though it just looks like 0.3 degrees centigrade or so. And this cooling slowly disappears over several years, and then you get back into natural variability. So volcanic eruption, volcanic radiative forcing is a natural forcing, and you can compare those to other kinds of forcings that have happened. So if you think about ice sheets and vegetation during ice age climate forcing, so global radiative forcings during the last ice age relative to the current interglacial period, the total forcing is these three numbers, so minus 6.6, and there is some uncertainty in estimating these, so plus minus 1.5 watts per meter squared. Thus 5-degree cooling of the ice age implies a climate sensitivity of 0.75 degrees per 1 watt per meter squared forcing. Again, we haven't defined climate sensitivity yet, but I will define it in the upcoming podcast in this chapter. So what I'm saying here is that the natural forcing that induced the last ice age and also led to its termination, triggered by orbital parameters that we talked about before: obliquity, eccentricity, and precession. So once the ice age sets in, then ice sheets grow on land, albedo changes, vegetation changes, so that creates a forcing. There are changes in carbon dioxide, methane, and N2O as well, which also cools, so it's a positive feedback. And aerosols, dust amount increases, as I mentioned before when I mentioned ice cores, so that also cools the climate. So altogether there is a minus 6.6 watts per meter squared, and we can compare that to other types of forcings we have had since the Industrial Revolution. So we are looking at radiative forcing as a function of time since about the Industrial Revolution. So we are looking at well-mixed greenhouse gases like carbon dioxide. So they have been creating effectively a positive forcing, which means they are keeping more energy in the system. Ozone is somewhere here. Stratospheric water vapor is in there. They are all above zero here. Solar irradiance has made a little contribution. I will show a little bit more detail. Many people blamed solar irradiance, natural variability in the energy output from the sun, which changes because of things called sunspots, which have a 11-year cycle, and they can change from century to century, and we'll see that that doesn't explain global warming. Land use change, which is negative, which means the net effect of deforestation, urbanization, and so on has been to increase the albedo and cool the temperatures a tiny bit. And snow albedo, which is one of these lines here. The colors are not terribly clear here. So reflective tropospheric aerosols are here. Stratospheric aerosols associated with volcanoes are in here. You can see the spikes. So you can see El Chichon, Pinatubo, Agung, Krakatau, and the other one. Okay, so aerosols indirect effect, which means aerosols can directly block sunlight, but they also have an indirect effect where they act as cloud condensation nuclei. They change cloud optical properties or albedo, they change water droplet size in the rain, they change the dynamics through these radiative effects as well, microphysics effects, which are called aerosol indirect effects, as opposed to direct effects where they are just blocking sunlight and creating solar dimming. So a summary is always created by the Intergovernmental Panel on Climate Change. This is from the last assessment, which was released in 2014. The current assessment is sixth one is now in release, started already in 2021 and will continue into 2022. So here again looking at natural forcing of solar irradiance and looking at anthropogenic emissions. So here we have carbon dioxide, which is positive at around 2 watts per meter squared. Other greenhouse gases well-mixed greenhouse gases: methane, N2O, and halocarbons, CFCs, HFCs that we mentioned. Ozone, in the stratosphere it cools. In the troposphere it's a strong greenhouse gas, as we said. Stratospheric water vapor can trap outgoing energy and doesn't directly affect the troposphere, but it affects the dynamics and radiative balance. So that is from methane. Surface albedo, land use is negative, as we saw here. Land use is cooling. And black carbon on snow is creating black carbon is black because it absorbs light. So when it absorbs sunlight, it traps energy, and if it falls into glaciers and snow, then it accelerates the snow melting and causes warming. So you can see that effect here. Contrails are produced by aircrafts, and they create these clouds which allow solar radiation to come in but trap the outgoing long wave, so they have a tiny bit of warming effect. Aerosol radiation interactions, a cooling effect. So aerosol cloud interactions, a cooling effect here. So you have direct and indirect effects included. So the total anthropogenic emission is over 2 watts per meter squared over this period of 1750 to 2011, which means the balance at the top of the atmosphere in terms of incoming short wave and outgoing long wave has been changed, and we are keeping more than 2 watts per meter square additional energy into the system, which is causing global warming. Okay, so here is total solar irradiance. You can see the 11-year cycle here, put together with multiple satellites over a few decades, and you can see the total solar irradiance in watts per meter squared, how it has changed over time. Solar physics is somewhat straightforward, and these can be measured and computed. Basically, sun is a fusion reactor. Hydrogen is going through fusion, producing lots of energy and becoming helium. So helium is heavier, so it increases the gravitational pull to the center, but the energy released expands the sun, so sun is constantly expanding. And you can see that in terms of number of watts per meter squared, it is not big compared to the anthropogenic forcing. So the contribution of solar irradiance to warming, shown here, for example, total solar irradiance in watts per meter squared in degrees Celsius. You can see that the recently, when warming has accelerated, the solar irradiance has dropped off. So if anybody is telling you that solar irradiance explains global warming, then be sure to show them this graph, because it was adding to the warming from the Industrial Revolution to about the 1950s, but since then it is not a contributor at all to global warming. Okay, so we will leave this here and then come back and look more specifically at the very complicated feedbacks that are in the system. Many positive feedbacks, which means they amplify the warming. Many negative feedbacks, which means they damp the warming. So the net warming is a combination of these, and there are ways in which we can see whether a system is net positive or net negative, and I'll explain what that means in the next podcast. Okay.